Okay, so we will finally start looking at the infrared physics in 4 dimensions. Again, we will today we will focus on classical physics and some of these interesting results which have been obtained in recent years. And probably, in my opinion, one of the most important result is by Ashok, Bishwajit, and Arnab, who is sitting right here in 2019, that we will discuss. And then from next lecture, we will go to this subject of asymptotic symmetries and then finally quantum soft theorems. And so let's just start with let's just recall the thing in d greater than 4 dimensions quickly. That as we saw, that if I look at the radiative part of the metric as a function of frequency and the angle of the detector, then this has this interesting universal structure. So I'll just write down once the formula to recall, which was up to some normalization that I'm just ignoring. that was already included. Summation over all particles. I'm being little schematic here because we have done it, so I'm not separating in and out particle because we already derived the formula in detail. But whenever I write n plus m, just assume that we have all the particles. And if I write, wherever there's a need to separate, as we will see, incoming and outgoing, I will be careful. But since we did this carefully last time, I'm just being a little fast here. Where k, as just to remember, k was simply omega 4 vector omega 1 n hat. So this was the result we saw was universal in d greater than 4 dimensions. And in the end of the last discussion, we just briefly saw that where is the first change which will come in this, because of the fact that intuitively the angular momentum for a particle will scale as log of t at late time as t goes to plus or minus infinity. And so that will clearly make a change here, because this will give us some divergent contribution. Oh, thank you, yeah. E, yes. And this will clearly give us a divergent contribution. So we need to analyze the effect of this. So what we are going to first do is what we actually did, how this thing was happened. So we will make an educated guess in the sense that we just analyze some specific trajectories of particles and see how this kind of behavior emerges. And then based on this, we will make a guess for the formula. Then we will check the guess against known results in classical GR. So, there are some complicated calculations that relativists had done to study scattering, but they couldn't, of course, they couldn't find, if omega is finite, you can't find closed form formula, but you can write some integrals, some integral forms for this radiation. And then we would see that if you take soft limit of those formula, it will match with what our educated guess is. And finally, since the educated guess was working, Arnab, Ashok, and Bishwajit decided to just prove it along the lines of how we saw our proof last time. But of course, the proof is significantly more complicated, and then they came up with a universal result in 4D, which I will write down in the end of this discussion. So the first thing is, so the logic of this discussion today is we first make the educated guess of how this formula changes in 4D. Then we will test this against some known result. You will see what I mean by this. And finally, I will summarize the proof of S cube, where S cube is Saha, Sahu, and Sen. And this is still the remarkable thing about this result is that it's completely robust, and it is one of those. It is like this result, which that will not change. I mean, now we have a full universal result beyond the leading order in 4 dimension for any scattering involving any astrophysical objects. Okay, so let me start by making educated guess first, and then see how this formula can change. So we are going to start with a very a simple setup first, so that so we will take a specific example of scattering and try to analyze how this J first changes asymptotically. So is there any question so far, by the way? Is it fine? Okay, so let's start with a test case which will help us make an educated guess. And the test case is what is called probe scatterer limit. And so the setup is the following pictorially, that we have a heavy star of mass m0 and we have some probe particle of mass m, and we want to study the scattering of this particle in the limit that m0 becomes very large, in the sense m0 goes to infinity, so that the radiation is only being emitted from this particle. That's what we are interested in studying. So this is called a probe scatterer approximation. So it's a limit if you do this, but if you expand in the inverse power of m, it's the approximation. And it's in the GR literature, this is called extreme mass ratio approximation also, where you have a small black hole which either scatters or plunges into a large black hole. So the advantage, why do we do this? Because first of all, there are only 2 particles in the incoming state and the outgoing state, and one of the particle doesn't radiate at all. So it just simplifies our life, right? So the simplest possible case where we could analyze scattering, gravitational scattering. And so I'll make a choice of a frame. So let's say that we are in a so all the momenta of this object we will denote as capital P, and or maybe that will be confusing. Maybe I'll call it P probe, and P scatterer, and this one P probe. So this is the frame in which we will work. So P scatterer at the initial time. So when these are some notations that it will be obvious upon inspection. When I use minus, means at t equal to minus infinity. So the incoming momentum of the scatter, we simply choose it to be, because it's at rest, the object is at rest. And then the P probe minus mu is some E1 P1, P probe plus mu is E2 P2, and P scatterer plus mu is minus m0 minus E1 minus E2. Sorry, I'm just writing standard kinematic just so that we have something to work with. So this is our setup. This is our kinematical setup for the probe scatterer approximation, and we do expansion in m0. So whatever terms comes as 1 by m0, we suppress them. So first thing we do is we take this guy and then we substitute it in this formula right here. Is it clear? So we take that and we substitute a formula right here. But we can, before doing that, let me make a small choice for our gauge. So as I'm assuming that we know that students have studied linear gravity. So the object that we are working with is not this metric, but the contraction in some sense of epsilon polarization with E. So let me just call it phi. And we can always, there is a gauge. Please ask if something is not clear. There is always a gauge freedom in this, in the sense that epsilon mu nu, if you change by for any vector zeta, then the physics doesn't change, simply because E satisfies the equation. Remember, we were in the harmonic gauge. It's just word identity, because E satisfies um, equal to 0. So this is a purely a this doesn't change our physics, because if you contract this or if you contract this whole thing or this thing, nothing will change because of this as he said, word identity. So it's classical theory. So I didn't use the yeah. You're right, but yeah.
If you wanted to model in a realistic framework that this star or whatever should have been in an expanding background. So
Exactly.
Background.
Yeah.
In which case you shouldn't have had the energy conservation.
That's an excellent point. So, well, I mean, we could always say that we have an approximate energy conservation where the loss of the energy is parameterized by 1 by the cosmological, the proportion to the cosmological constant. So, even in expanding universe, I think the formulas we find, I think they may be still valid. I mean, I don't know immediately if something will go wrong non-perturbatively. This is our intuition that it's because the cosmological constant is very small, to excellent approximation, we can approximate the de Sitter as in terms of flat plus correction.
The stars that we are actually observing, those were from
Yeah.
an era where we had radiation domination.
Correct. Yes.
So it's not really, the scale factor is not really the de Sitter factor, it's time dependent.
But that's it's quasi de Sitter. So because it's quasi de Sitter, it's slowly varying, right? So I mean, I'm agreeing with you. I'm just saying that there is of course a underlying assumption here that the flat space physics is a good approximation to the actual answers when we are in de Sitter.
The flat space should become a better and better approximation when, I guess.
Well, even if the scattering was happening in a patch of de Sitter. So people do study these. These are called de Sitters of theorem. So the point is that this was studied by two postdocs in TFR recently, Sayali and Diksha. So what they showed is that if you look at scattering in a small patch of de Sitter, so that the patch is small enough compared to the scale radius of de Sitter that it's approximately flat, then you see that there are interesting corrections to the soft theorem, but and they are a bit puzzling in their own right, but some of this result remains valid. So they are puzzling in the following sense, that you get terms which are proportional to 1 by omega square, because of the fact that you get 1 by omega times these kind of terms. So they look like they are more soft than what we find in flat space physics, but then they have other scale which. So now it's a bit of it's not entirely clear like what to make of this as far as soft expansion is going. Like
Lambda here is the cosmological constant.
right, it's the infrared scale, exactly. Yeah, inverse of the radius. So so you do find such corrections, but the 1 by omega term remains this plus extra corrections in lambda. So that's the closest we know what effect of de Sitter is on the. But I should say that this is just one paper, and I think more needs to be understood about the.
I mean, if you are worrying about de Sitter effects when de Sitter was strong, then would you even try to base the analysis based on flat space asymptotics?
Yeah.
You wouldn't do that, right?
Yeah. So that's a different question for which we are even in a less satisfactory domain, because right now we are not really worrying so much about the asymptotics in the sense that we are I have never talked about compactification or anything like that. So
I'm just asking a question that things that LIGO or
yeah, so their entire waveform analysis, right? It's in flat space. For example, and all the theoretical waveforms are in flat space.
is that justified? I mean, the corrections are
Yeah.
to be small.
Yeah, I mean that's expected, and I think that the way they even parameterize the effect of de Sitter is subleading effect in their theoretical waveform. So I think that, but again, because of this Diksha and Sayali's work, that there are these puzzling terms which arise, and I think they need to be better understood also. So I think your question needs a more serious, investigation.
But there is one issue. Scattering is fundamentally a global discussion, right?
Yeah.
So, I mean, you cannot get away from the question that he's asking.
You cannot get away. You cannot get away.
At least for a class of physical questions,
Yeah, so I think here the underlying, here the physics, yeah.
Scattering happened recently.
Yeah, no,
Then you're
yeah.
okay because you're in flat space. But if you're looking at signatures,
From, but because the curvature is, because the cosmological constant is small, we hope the corrections are, I don't have anything concrete to say. I'm agreeing with you, but of course, let's look at LIGO modeling, right?
it's
So,
not to put you in a spot, it is a discussion.
yeah, no, I know, but I'm saying that it's a question which we don't have then we would question LIGO also, right? Because LIGO is looking at very old black hole in spirals and their modeling is completely in flat space. So I think.
I don't know that flat space had not set in those spirals. Is it known?
So we are finding more and more merging events, right? Which would have happened, I don't know, someone else may better in the far past, right? So, yeah, we should ask an astrophysicist. But here, of course, the point also is that I think that this, especially Diksha and Sayali's assumption was that you are right that if you study this, they want to restrict scattering in a patch of de Sitter, like a space-time patch of de Sitter. So the point is that somehow if you want to study scattering at very late time, then de Sitter effects obviously become important. So here you are saying that somehow the detector switches on at some time after the heavy scattering has taken place, so that you can restrict your attention. So the radiation you are measuring is from that region of space-time only. Then your detector switches off. Like I think if you keep so there is now new thing that Wald and his collaborators have done called de Sitter memory, which is really an infinite time effect. And that really you do see a difference. Like that is not something that can be, I think, approximated simply from flat space answer. So what you are saying, right? It's a global question.
Yeah, because fundamentally scattering is, wave scattering is,
Yes.
the maths that we use uses global properties.
Exactly. No, I completely agree. Yeah. So I think that this is really all in flat space, or asymptotically flat space, and I think that if we are in asymptotically de Sitter space, then we really have to, we don't even know how to set up, except I think now this new work of Loga and his collaborators are the only one I know where they are looking at actually radiation from, by looking at global properties of de Sitter. But I'm not sure if they have analyzed the soft radiation. Yeah. Sorry. So now because of this freedom, we can just set epsilon 0 nu to be 0. That is, we can always fix this gauge, and so that means that our polarization only has spatial component. This is just for convenience. It's not to. It just makes our life easier in simplifying the formula. And then it turns out that if I use this gauge, and this you can check in a paper that we wrote with Ashok in. So the explicit. So what we want to do is use this, substitute this here, and do a 1 by m0 expansion. Okay. So you will get terms. You even at the order m0 to the 0 order, you get terms which because you will have to Taylor expand this. In this, you write PA dot K for the scatterer. In terms of this, you do some Taylor expansion. You get some messy terms. So those terms are always proportional to epsilon 0 nu. So you can check that if you use this Prof scatterer approximation and use this transversal, transverse gauge, then the formula for this soft factor in this approximation simplifies to simply the contribution from the probe. So it just gives us PA. I should have put probe. So plus minus of course means the initial and final according to our convention. So I hope this point is clear, that for the probe scatterer approximation in the traceless transverse gauge, the formula for the universal result in D greater than 4 dimensions purely gets a contribution from the probe asymptotics only. Of course, the final momenta and angular momentum of the probe depends on the presence of M0. So it's not like physics is independent of M0, but the contribution of the asymptotic momenta and the angular momentum of the scatterer are suppressed in this gauge. Okay, it's just for convenience. So this is the formula that we have now in D greater than, in some sense, this is the 0th order formula, and now we want to evaluate J at late time for the probe, and that would give us an educated guess. So I hope the logic is clear, and so now let's do that. And now this is something, of course, that we
If I try to write this in a general gauge,
yeah.
is it what?
It's a bit ugly. I mean, because the point is that you get terms. You see, like if you just start writing this down, then for the scatterer also, the final momentum is of course non-trivial, and so then you get terms which are where you have to do Taylor expansion in 1 by m0, and so then you get terms of the form like some epsilon 0 nu, and they are ugly. Like you get PA0 PA nu by PA dot K PA nu by PA K0 square, something like that. I mean, some kind of complicated terms, but they are all proportional to epsilon 0 nu. So I just want to not write them because physics is not changing. Na? But if you, in our paper, we have written most general formula also. So I'm just for this lecture, I mean this discussion, I'm restricting. Yeah. Okay. So now let's study the trajectory of the probe asymptotic. And so the initial trajectory is so 0 is the time component, of course, and r is just the displacement vector, and it's we are thinking of this as the inertial time, not proper time. That is why this is just t, right? Not so this is some, let's say, a minus plus beta minus t in d greater than 4. This would be the trajectory, and the trajectory for in the future would be right. I mean, because they are free particles, right, in d greater than 4. But in, of course, d equal to 4, because of the 1 by r potential, we know that this thing get modified. And so, the modification, of course, is that the 0 component, of course, won't change, but and similarly r plus okay. So now we substitute this. Now we immediately see that if I now compute the let's assume that, sorry, I should have said this, let's assume both the particles are scalar. This is our setup, and both the objects are scalar, so no spin, no intrinsic spin, and so then the only angular momentum is the orbital angular momentum. And so now if I compute orbital angular momentum, then you see that maybe can I erase this part? So then if I just compute the orbital angular momentum, we immediately see that they will get, so let me compute the initial angular momentum first. So j minus, let's first compute the ij component asymptotically. Then you see that it will give us So I'm writing the divergent component first. So it will be the component proportional to log t is simply coming from d minus I beta minus j minus d minus j beta minus I. Yeah.
You're using dimensionless coordinates or is it dimensionful?
So beta is v by c. Beta is v by c.
No,
C is 1, sorry.
If you take log of t,
Yeah.
what it is
Okay, that we will clarify. So this log of, thank you. So this log of t, by log of t means, of course we mean compared to some scale as you are saying. Okay, so in this case, for example, let me take Schwarzschild radius of m0. But because it's log, we will see that, okay, so what I mean is this is t times m0. The reason I did not write m0, I mean, even though it's incorrect, is because this is, when you go to frequency space, what is important is, I mean, this is like log t plus log m0, and what is important is the log t divergence part. So always m0 is sitting there, it's just that, like that. So, but I'll just suppress, but what we will, right, I hope it's okay, I mean. In general, this is for this question, this setup, in general it will be the, whatever is the roughly the size of the scattering region where the dominant scattering is taking place. So that is what will replace this Schwarzschild radius. Log mod t. And okay, I'm just writing for completeness now, so, sorry. And j, what as you will see, probably little important is j minus 0I t, which is which will be simply the R0, so it will be minus and I mean, when I write this plus order t to the 0 terms. So of course there is a finite term, right, like for free particle, but I'm suppressing it because my concern right now, our concern is to understand the modification brought about by the log terms. Is this clear? So of course if you, the A cross B will give us the order t to the 0 term in the angular momentum, that I have just not written down because they are the one that are not, they are ordered, they are finite, so they are subdominant to this at late time. And similarly, j plus 0I. Okay, so we already see that this effect is there this is the, so clearly now if I just substitute this in our formula, then I have a divergence, right, and that totally dominates over the finite term, whatever the finite terms are. So the question is whether is this actually correct, this kind of naive, in some sense a very brute force substitution where there is clearly a divergence. Is it really what comes out of a systematic study of radiation? That's the first question. And the second question is how universal is it? Because right now we are looking at a specific case of some probe and some scatterer, etc. Right? But this helps us with the educated guess. And so let me make one remark which will be clear. Maybe I say a little bit more about this. That in the probe scatterer limit, one can explicitly check, this is just some GR computation, that DI is actually proportional to the let me call it. So one can explicitly check, if you study just equation of motion of a probe particle in Schwarzschild at late time, you just study the trajectory, you can see that you can compute this D, and this D turned out to be linear in beta, proportional to beta, for the specific case. So for the specific case, you see that, so if this is true, these terms are 0. So this is 0, and this is 0, but these two terms of course survive. right? So that's just as I didn't have to. I mean, just for completeness. Again, this detail you can see the expression for this in an older paper. Where we made this educated guess. So anyway, so let us, I will give expression of this in a minute when we do this, when we compare this with the GR result. But once I substitute this and I write the log term, then it has the following form. So let me just write that. And then that's our guess formula in 4 dimensions for the probe scatterer approximation. Then we have to check whether someone in GR had done something like this and we can compare. So I just substitute all this. Is there any question about this right now? Right now it's just only d greater than 4, so that's why we are making a guess. Yes. Yes. Yes, that's the educated guess. So that's not, right now we don't have a theorem. So that's what the logic I was explaining, that we do this, substitute, the dumbest thing we would do, we'll get some formula, then we will first check it against some known GR result, if there are any GR results available. If they agree, then it gives us some confidence. And then Arnab and Ashok and Vishwajit proved that that's actually the rigorous way to do also gives us this result. So, so this is how we did it. I mean, we first just guessed it like this because we didn't have the theorem. Yeah.
What you did, I mean, the steps are maybe in your paper, but what you did was to just look at the trajectory of a light particle.
Yeah, that is yes.
Of a heavy particle.
Yes.
The asymptotic form of
Yes.
long ago and long after.
Yes, just our usual 1/r thing, right? Like so that is of course known from much before and standard. Yeah.
But from there, then you computed just the angular momentum of what?
Of the probe
of the
the small light particle.
And the outgoing light particle.
Yes.
And that has a log theta.
Yes. And now I just substitute.
So this is this calculation, I said, because it's just the scattering of one particle against the other.
Yeah.
Makes no reference to any radiation.
Right now, no. This has nothing to do with radiation.
That's right.
Yeah, exactly. Now we use that as a data to feed into our universal formula of radiation in d greater than 4 dimension, and then we see what we find. So then once we substitute this, we see that so I'm just writing the final, no, not this, sorry, apologies. I'm just writing the final result. And so now I hope I'm not explicitly telling, but now for this example, the sum is only over the probe particle, and then we get maybe I will just write it as where this beta is just the 4 vector for this beta, and then I should have, of course, but each of them should come with a gamma for making Lorentz covariance, so there should be an overall factor of. So remember, I'm simply substituting P. It was P mu P nu by P dot K. I'm just writing in terms of beta, and we get one overall factor of beta like this. So this is the leading term, which is 1 by omega. Remember, K is omega. And then the next term, which is the one that we are interested in, it turns out to be it's just the I will explain the notation in a minute. Sorry, I should have used n cap here. Okay, so this is now just substitution. You take these things where j's are 0, only j0i is not 0, you just substitute it here. You are only contracting this with epsilon ij, and now you just substitute and you find that you get this as the extra term, where n cap is just, remember, the unit vector like that. So this looks a little ridiculous at this level because we are supposed to get a radiative field in the frequency domain, but then naively it looks like we have some term component which is proportional to the time. But then the only way this formula at the level of educated guess would make sense is if we replace mod t with omega inverse. And there's a hope that this may be correct because we are looking at soft expansion, and this was a correction at large mod t. And so, there is no other scale in the problem which could substitute for large mod t. So we can make this as a guess. So this is a guess. Okay, and so now we want to see if there are some results in classical GR against which we can make this, verify this guess. So that is the absolutely remarkable work in 70s by Peters, who did the following. Capital, say that again. The capital D? Capital D is, as you see that if you have a particle moving in the background of Schwarzschild, then if you compute the asymptotic trajectory and you look at coefficient of log t term, you can check that it's actually, so this D is a vector, it's actually proportional to beta. And that coefficient of proportionality is what I am calling capital D. So capital D, I will write the formula for it. It explicitly depends on beta A and the mass of the Schwarzschild. Maybe I can just write it here. I mean, so dA turns out to be equal to so this just comes from looking at just asymptotics of a particle in Schwarzschild. So it's of course done in many books also, GR books. Okay, so here is what Peters did. He looked at the same setup. And his paper is called Gravitational sorry, I don't remember Bremsstrahlung spelling, so I will just write it like that. So then there is so he exactly look at this. There's a Schwarzschild metric. So there's a mass m at the center of the space-time and a probe particle m, which is scattering at impact parameter b, which is much larger than the Schwarzschild radius. And then he asked, okay, so this particle will little bit back react on the metric, and as a result it will radiate. And so we can he asked a question about, can we write down this phi omega n hat at least in some analytic form? So of course in general for finite omega, this as you would imagine, right, how would he do it? So what he found was some integral expressions for this thing. So it was basically some complicated integrals. So I won't write more details of this, but it was in some form which had some integral over the trajectory of this particle and some and these are very, very horrible integrals. I mean, there are more integrals inside because there is a Green's function. You have to look at Green's function of Schwarzschild when you're computing radiation, and that is very, very complicated. And so all that was included in his formula. So his formula, if you see his paper, it is like sum of 4 terms. Each term is a horrible integral. But now we could, we can ask, okay, so we take this formula and then we look at the soft expansion, and can we actually do this integral in the soft limit? Now if you take if you look at the leading term in the soft expansion, then you see that you immediately get back this term. So that is encouraging, but that is also expected because we know from a long time that the leading term in radiation is always this particular term. And then we in our paper we did a systematic analysis of the subleading term of this. Then we found the following result. We got this answer plus an extra term, so that I'm just going to write down. So we get this plus, so the Peters, so let me call it phi bar actually. So phi bar omega n cap is of the form phi omega n cap plus an extra term which I just write down, which are the following form. Okay, so he found this plus an extra term. So now the question is why, so that means what? Is this formula inconsistent? Because we don't quite get this result. And then a little bit of thought reveals that actually it's not inconsistent, we missed something in the, because we anyway made a guess. So, in making this guess, we missed one important component of radiation, which is called the drag effect. So let me explain that. So when we make the guess, we were a little bit careless in making the guess, and the carelessness was what goes under the name of drag. And the drag effect, I will first explain it intuitively and then tell you qualitatively what the effect is. So intuitively, the idea is the following, that we have this m0 mass and a point particle, and it's radiating, but m0 has a curvature, and so this radiation slows down, because this also feels the effect of the curvature. So that slowing down of the radiation, that has to be taken into consideration. But that effect could have never been the way we did it here. It was not taken into consideration, because the only effect we took into consideration here is the slowing down of the particle with the log t term. So some of this extra term, where the radiation itself feels the gravitational Coulombic force, that was not considered. So that we have to consider. But that we know how to consider in this case. And so let me explain. Yeah.
I'm not a GR person, but
Yeah.
you mentioned that this impact parameter is far larger than RS. So shouldn't there be this effect of the curvature? Shouldn't it be less, because it is significantly away, so that the
Yeah, it is certainly less, but the question is whether it is significantly less. That's an important point. And as I will explain to you, that it exactly contributes to this order. So it is significantly less in the sense it doesn't contribute at leading order, but it contributes at this order. So yeah, that's an excellent point, that radiation is far away. Why should the curvature feel anything? But of course we expect it to, the radiation to feel some effect. The question is at what order in the frequency expansion it kicks in, and it's exactly as I will argue at this order. Okay. So let me now explain this effect, and that will improve our educated guess. And then that matches with the, so it's it's a bit of a back and forth. We did a guess, we got this, but then we check it against a absolutely remarkable result in classical GR, and we found that, okay, look, we missed in our guess one guess we should have also made. So that gives us an improved guess. So this effect is actually not very hard to understand, and the effect is simply because of the fact that if you look at, so remember how did we did the radiation? We worked in retarded time. So we went from t to u, because if a source emits a gravitational radiation, then it reaches at a later time, right? And that time was parameterized by u, which is t minus r. But this is in Minkowski space. If you are in Schwarzschild, and if you have studied tortoise coordinates, you know that actually this gets corrected as 2gm log r. And so remember that we had this in the formula in the first lecture, we had something like e to the I omega u. We had something like e to the I omega t, which we substituted. So please ask, okay, if I'm saying random things. So then we substituted this as e to the I omega u plus e to the I omega r, and then this thing came out of the normalization, if you remember. But now you see that there's an extra term, and the extra term is e to the 2gm 2gm sorry, it's not I will explain in a minute, just give me a second. 2gm, if you have a gravitational wave of frequency omega in a background of Schwarzschild mass capital M, then the retardation effect it feels will be of course proportional to the frequency, and that effect is given by 2gm omega log omega r. So this is a new term this is a, yeah, let me explain it properly, sorry. So this is the coordinate, and now we just substitute it in e to the I omega t. So we get e to the I omega u plus times e to the I omega r times e to the 2I gm omega log r. But of course, as you would have said, that log r is cannot make sense because r is dimension full, and so and r is large, right? We are looking at this as a large distance, so that means that the only compensating factor we could have, because we have no other scale in the problem which is small, which is inverse of r, we could have put omega r. So again, this is part of a guess, right? That it need not be omega r, but the only at large r we feel the dominant effect will only come from small frequency, so it's log omega r. So as a part of the guess, we include this term here. So what does it mean now? So in my phi omega n should get modified to my old phi omega n times this term. Is this part clear? At least is the argument clear? That we haven't done anything too deep. The overall phase, which was e to the I omega r, got modified because of the tortoise coordinates in 4 dimensions, and that effect is this one. Now if I want to, you see this term is proportional to, say that again? Yeah, that is if you are looking at it at a, that's what I'm saying. But if you go to large r, at infinite r, because we are interested in looking at the radiation at infinite r, so the capital M effect is suppressed. Right, so the effect which is like a dominant effect is this one. Because if its log is very large, the phase is just going to cancel, right? It's 2 to 5 oscillating. So again, this is part of our guess. We have to prove this rigorously. But if I make this as my guess, then you see that what is this going to change in my formula for radiation? If I now expand this, then the first term is 1, of course. So that gives me phi omega n. The second term is omega log omega times this term. So that is log omega times this factor, and that precisely turns out to be this factor. Okay, so that makes us help us make then our answer exactly match with the Peter's result, that the naive substitution of log t in J didn't help us catch the curvature of space-time, which is this effect. Is that point clear?
I think, but it's not about tortoise coordinate. Why is it?
No, this is just our usual large, you just do an expansion in Schwarzschild, then there will be a log r by r correction to the t minus r, right? At large r.
But why does omega come in there?
No, that is coming coming here in the phase.
Yeah, but now omega.
Yeah, that's right now part of a guess. That because we are at large r, the order 1 phase will only come if the r is the largest distance in the problem. So if your frequency is, the wavelength of the graviton, which is only of that distance, will feel this drag, otherwise it will not feel the drag. So if the wavelength is only of order r, it will feel this drag effect at large r. So that means it has to be omega, no? Right now it's at the level of argument, right? So I should mention one thing, that this effect is not taken super seriously by people in GR always, because this is simply, as we see, it's a phase. It's just an overall phase. And in the flux, this phase does not matter. So because we always measure flux, actually this kind of drop out. And so it is not important. But for overall theoretical consistency, that term is there. Right? So if you are only interested in flux, we would forget this term and we would not worry about it. But if you just look at the field, it's there. Does it answer your question? So I want the curvature. I am looking at what graviton feels the effect of the Coulombic force at large r, right? So of course the wavelength has to be of the order of r, of that mode, right? Otherwise it will not feel it. So then so that is 1 by omega, no? The wavelength. So that's all. Is that not convincing?
Yeah.
Okay. So now okay. So that gives us a guess for a probe scatterer, and now the point is that if this guess was true, then let me give first some implication of this guess, and then we write the theorem, which was proved by S cube. There are nice implications of this already, that we see that if I look at deflection-less trajectory, so I say that my particle is far and far apart from the star, so that the to leading order, so the velocity here is beta minus, the velocity here is beta plus. To leading order, so beta plus we know is beta minus plus some impulse. So suppose I do where this is proportional to g, of course. This is the expansion in g, right? Which we can compute order by order in perturbation theory. So if I look at the leading order contribution, then obviously you see that this term will drop out. Because if the incoming and outgoing particle are moment are same, and this is like an odd function of beta, and so with the appropriate sign, this thing just cancel. But if you look at this term, it turns out that d also changes sign. Because remember, d was proportional to c, which had a plus or a minus when I wrote down the formula. So this formula, even if if your particle have no deflection, it looks like there is a radiation. But this is expected because the radiation is really coming from the fact that the initial angular momentum has a log t effect. So even if I don't worry about the change in the velocity, there is already a radiation coming from early time and radiation coming from the late time, and they are adding up. Is that point clear? So there is a qualitative difference between these two effects. This effect is really related to the net change in the momentum of the scattering particle, whereas this effect is really there is an early time radiation and the late time radiation, and they are adding up. That is one thing. And the second thing is, you may worry that what if beta goes to 1, then it looks like my all these factors are diverging. But of course there is a m here. So in the massless limit n by 1 by square, this becomes just the energy of the massless particle, and all these formula remain valid. So even though I have written it for a probe particle which has mass m, I can just apply to a massless particle where I will replace this factor with the energy of the massless particle. Okay, so this is a general formula for a massive or massless probe particle in the presence of a scatterer, like a Schwarzschild scatterer, for example. Right. So, so let me now complete this formula. Yeah, exactly. So the point is that you see that you have two particles, the star at early time at t equal to minus infinity, that is remaining anyway just static, right? And then there is other particle which is moving with some velocity beta, and now this has a Coulombic attraction. So this is accelerating at all times. That is causing the angular momentum to diverge and it also to radiate.
It's like the electromagnetic.
It's exactly the same. And so the point is that effect is existing by itself. So even if the particle momentum didn't change, there is always a radiation coming from here and radiation coming from here.
The momentum, the particle is moving because of the force the momentum has to change.
No, yeah, I understand. I'm saying that if you expand the final velocity perturbatively in the initial velocity, for this term, the leading order term of course cancels. Right? Because if the final velocity is equal to initial velocity, then this term just cancels. But this term doesn't cancel, they add up, you get twice. And there's adding up because of the fact that this radiation is not due to the net, like the net impulse that the particle is experiencing, but it's due to the fact that there is a early time radiation and a late time radiation because particle is just accelerating.
And the late time radiation is the early time plus the radiation it has emitted throughout its
throughout the thing. So if I take this beta plus and I expand perturbatively in beta minus and the impulse, then of course it is the early time radiation plus correction. Of course these formulas are interesting because they are non-perturbative in the sense that you give me initial and final velocities and these formulas don't change. Right? So again I think we discussed this earlier. I just want to insist that the final velocity of course depend on the details of the scattering. But the universality is not that we are given, once we are given initial momenta, we have final momenta, of course not. But once we are given them independently, these formulas are universal. Right? Yeah.
One more comment. Is
Yeah.
this where memory comes in?
I will explain now. This is the event shape part, which I think I will start tomorrow. This part is related to what we call the linear displacement memory. And this part is what, I will explain this. This is what we call the tail to the memory. And both of them are universal observables that we are now seeing, that in any scattering, their functional form is universal. So
I just
yeah.
So at least maybe another way to understand.
Yeah.
You could correct me if this understanding is wrong. Is that if you naively compute the quadrupole moment of this system,
Yes.
you would expect that there is no radiation, no gravitational
Yes.
radiation.
Yes.
But because the force is coulombic,
Yes.
there is a residual
Yes.
gravitational
Yes.
radiation that
Yes.
is always with
Yes.
you.
Yes.
And that is what you are picking
Precisely.
up.
That's precisely. Actually, I will discuss this exactly the point you made tomorrow when I discuss the event shape. Precisely in terms of the quadrupole moment. That this term we are picking up.
Quadrupole moment, if you just computed it for a particle going around in a, say, in a
Yeah.
circle.
If you go to n particles,
Yeah.
then we will have it, and that is exactly the origin of this. So once I write this S cube theorem, we would understand the corresponding terms in terms of quadrupole.
I mean, while it explains it mathematically, it does not make it less mysterious,
I agree.
right?
Yeah, I mean, not just mathematically, it explains it through, I mean, this we are proving it.
The fact that there exist physical systems in life where before you decided to start the experiment, it had
That radiation.
radiation and that persisted.
Always.
That always persisted.
Yes.
I mean, we can discuss this later, but our ideology of it is in some sense in conflict with the ideology of physics and the way we do physics experiments.
But that is really the memory,
Yeah.
what you are saying,
Yeah.
because that is the one that always persists.
Because
But this one, this one doesn't. This is this decays with time.
even the angular momentum that is there,
Yeah.
that is always there even before you started the experiment.
Yeah. I agree. Yeah. So you're saying why is it diverging? Is that the?
Why is it? Yeah, I mean, if it didn't diverge, you could presumably find a scale or some
Yeah.
way of setting up your experiment and
Yeah.
you see it.
Yeah.
But because it diverges, you will always know, in some sense, know about it.
Yeah. And I mean, you are right. That, and that's really the origin of at least part of this term. As exactly.
So,
Yeah. Go on. Yeah.
no, you want to eat, right?
You want to?
You want to eat, right?
Oh, okay. So maybe can I take 4 minutes? Okay. So so let me just say that this d is now modified to d bar, which is d plus this extra term coming from m log omega times the leading thing. Okay. By the way, just for people who obviously will be familiar, this is called Weinberg's soft factor. This particular term. It's not important for us right now. When we do the quantum soft theorems, we will be more explicit about the nomenclature. Okay, now, so this guess, be encouraged by this guess, S cube looked at the same setup we discussed yesterday, but in 4 dimensions. So you have some scattering region, you have some particles coming in with some momenta and spin. And then there are some objects go out with some momenta and oh, thank you. Yeah. So I'm about to discuss it now. So here because of the fact that one of the particle is very heavy, that contribution is not coming. But let me explain it here. P m prime sigma m prime. And now we study the same thing. Exactly what we studied. We want to look at radiative field, but we want to do everything in 4 dimensions. So the proof I gave you yesterday in d greater than 4 is orders of magnitude more simple than what happens here because of these infrared effects. But the final answer is equally remarkable because it's universal. So let me just write the answer, and then we can discuss it more tomorrow. And I just answer Justin's comment. So this is the S cube. It's called a log soft theorem, and this is the final answer. So for the E, right, we write it as E. So now we don't have to take some particular polarization or anything. I just do the, and so it turns out to be. So now I'm going to start putting all the factors carefully, including the 1 by r, which is the fact that we are at the radiative field. just to be complete. So all the particles which are incoming, okay, and then I'm still continuing. Sorry, the space I ran out. So this is the contribution from all the incoming pairs of particles. So take all the pairs of particles between these, and then this is the contribution to the. So I'm only writing the log part. Okay, sorry. I'm not writing this part because this part doesn't change. So I'm only writing the log part, and so you see that this coefficient, which is a contribution to the log radiation from the incoming momenta, it doesn't depend on any other multiple moment. It only depends on the linear momenta of the scattering particle. And similarly, the same formula for the outgoing, C naught equal to D, CD equal to 1 to M, and everywhere you see a P, you replace with a P prime. And also the relative sign is plus, which is what ensures that there is no cancellation even if the initial and final moment are the same. And the drag term, which was the term that is here, that is an additional contribution. So let me just write it down. It's minus actually. 1 to M, the outgoing. So now I'm being a little, okay, I will write it. So this is the universal logs of theorem. It is universal because for any theory, not just Einstein's equation, like we did in a higher dimension, any theory of gravity, you compute the low frequency radiation. The first term is of course this one, and the second term is, the first term is what we wrote in higher dimension, and the second term is this one, which only depends, in fact it does not even depend on the spin of the particles, only depend on the linear momenta of the particles. And this term is the term which in the simple case of probe scatter gave us the drag term, the drag effect. Now I want to mention one small caveat because some important question were raised about it. So both these terms really come with, I have written log omega, but really both these terms, if you look at the derivation carefully, these two terms, they come with log omega b, where b is the scale of the characteristic scale of the scattering. Whereas this term comes with log omega r, where r is the distance of the detector. So that is why the which is exactly how it happens here, right? The term that come out. So at the level of log omega, they are both contributing, but the structural dependence on dimensionless parameter is different for both these terms. Okay, this depends on the detector distance, this on the scale of the system. Okay, so this is the full S cube logs of theorem, and just what Justin raised that when they derive this, the contribution, so we are looking at contribution to the radiation from the stress tensor of matter plus stress tensor of gravity. And what they show is that the asymptotic stress tensor of matter of course contributes here, but even the stress tensor which is contained in the Coulombic modes of the gravitational field, that leads to a contribution here. Now you may be puzzled that why is the gravitational stress tensor not field? But the Coulombic part of gravitational tensor is completely fixed by the particles. So the radiative part of gravitational stress tensor, which was, we had this, if you remember in the d greater than 4, we had this a mu nu by a dot n cap, which was a contribution. No such contribution can give a log. So there is no contribution of the radiative hard gravitational radiation to the logs of theorem. Whereas there is a contribution to the leading term as we discussed yesterday. Is it point clear what I'm saying? Sorry. So I think that was Justin's, your question, right? So there is really no other contribution. There is a contribution of gravitational tensor, but also only of the Coulombic modes, which comes here. And so tomorrow we will see how this effect and the leading effect give rise to some interesting infrared observables, which we call event shapes, including the memory. And maybe we can continue here from here. Massless or massive? Yeah, so we just, it's an object with momentum and multiple moments, but it's absolutely remarkable that this formula doesn't depend on the spin, even spin. And there was a conjecture that I will discuss tomorrow, that S cube in their paper said that even the term after this in the log expansion, so of course if you do the expansion of the radiation field in 4 dimensions, I will just take 1 more minute. So the structure of expansion looks like this, which we now understand very well. There is a 1 by omega term plus this logged omega term, plus there is a term which is omega log omega, which is clearly subleading to this term, plus order omega to the 0 term, plus there is a term which is omega log omega square term. Now S cube had conjectured based on some arguments that we will discuss tomorrow that this term is also universal, and they had guessed a form for this term also. And then in 2020 Bishwajit proved that, Bishwajit Sahu proved from first principle again that matches. So this term is universal, this term is universal, only depends on the momenta of the particles, and as Bishwajit showed that this term is also universal. It's more complicated, it has some more triplets of A, B, C, but it is also universal and only depends on the momenta of the particles, not even on spin, whereas these terms depend also on spin. So they are not universal, these are universal. And there is a conjecture, not conjecture, but maybe there is a very distant conjecture that all the terms which have this form in the expansion, they will be universal. Like this, we don't even have a conjectured expression for this. This was some, this is a conjecture. No, I shouldn't say conjecture. This is expectation of Sayali based on some studies in electromagnetic scattering many years ago. So it's, but and her expectation was then, of course, verified for both electromagnetism and gravity up to this order. But if such structures emerge, that it would be quite remarkable. There is a hierarchy of these terms in soft expansion, which don't depend on the details of the theory, which is a mysterious structure in itself that comes out. So this is called okay. Anyway, let me stop. We can continue tomorrow. I am only discussing gravity, but there is a slightly simpler but very analogous looking term for electromagnetism also, and even that is universal.
So there is no spin dependent universal?
Yeah, all the terms which are spin dependent are, omega log omega piece is not universal in the sense, it doesn't depend on the higher derivative correction to the Lagrangian, but it depends on the quantum, it depends on the momentum and the spin. So it's a slightly non-universal in that sense. So there is a form for that has been derived by is it Bishwajit and Devodina. for omega log omega also. So we see how much sort of quasi-universality it has. But these two terms are completely universal, exactly as the memory. Like there's no less universality in these terms compared to the memory.
Sorry, and spin dependence comes at what order?
At all different orders. So as we saw, omega to the 0 certainly, like this in d greater than 4, that depends on the j.
So
But
that's the first
no, this one also, if you look at omega log omega,
that's the first time that the spin dependence.
that's the first time the spin dependence comes. So
Basically, there is no hope of verifying string theory using this.
if you look at string amplitudes in higher dimension, then you can look at soft theorems from there, and they are consistent with the higher d greater than 4 soft theorem. So
May I ask, why would you expect string signatures
at higher,
extreme or higher?
yeah.
I mean, at what order? I mean, if you could cleverly subtract off these.
No, that's a very good point. So the point is that if you go to say order omega cube, then there is no factorization, because as we discussed yesterday, or actually order omega square, because of the fact that hard scattering details become important. So that's where the stringy, higher derivative terms will start kicking in. So, but those are not, we don't call them soft theorems, because they are not they are not, we call something in a radiative data theorem if it depends only on the asymptotic states of the scattering objects. So anything that depends on the bulk scattering, it's different, right? It's a different, we can't write formulas like this, universal formulas for them. So in that sense, the spirit of soft theorem is orthogonal to looking at the hard dynamics. It's really like a different thing altogether, different expansion altogether, because we are doing expansion in the frequency of the detector as opposed to coupling. So it's a complementary perturbative expansion.